So good evening all. I'm Pramod Gaval, research scholar, Department of Chemical Engineering, IIT Guwahati. So I'm a teaching assistant of this course, Mass Transfer Operation 2. The course tutor is Professor Chandanda, same department, IIT Guwahati. So I'm going to take a problem solving session 2, week 2 on humidification and air conditioning 1. So I think all of you have gone through the week 2 lectures which are available on SWAYAM portals. So here is a brief recap, the stoichiometric chart and its use, then cooling tower principles and operations. So first is a image show the stoichiometric chart for air and water system at 1 atm and 1 atm total pressures. So this is a graph, temperature versus different quantity like enthalpy, humidity, volume. Here right side the absolute humidity, right? So based on these graphs, we can calculate the adiabatic saturation temperature, variable temperature, dew point temperature, and also we can calculate the enthalpy at saturation conditions, right? So here the this denote the means last means 100% humidity means saturation humidity. So here is a different graphs denote for the relative humidity like 2%, 5%, 10%, 20%, 30%, right? So here is a figure to be show the reading the humidity chart. So here is a temperature versus humidity. So here is a TG means dry bulb temperatures. So at this suppose TG. So here we have to go through the state. Then uh, you have to draw the line parallel to this adiabatic saturation curves like this one, like to reach the 100% saturation. After that, draw the line to towards the temperatures axis, means x-axis. The temperature gets so TS, that is the adiabatic saturation temperatures. So which are generally adiabatic saturation temperature equal to the variable temperature TW. So here is a particular humidity or enthalpy, like for so at particular means particular dry bulb temperature and humidity. So here, so we have to draw the straight line here to 100% humidity. Then draw the line downward toward the x-axis. That's the dew point temperature, right? So for examples, like take any temperature like TG is equal to 30 degrees Celsius, right? And humidity take like this one's y is equal to 0.02, right? So we have to calculate the adiabatic saturation temperature and the dew point temperatures, like so here is a 30 temperature, go upward. Now here is a 0.02 kg of water per kg of air. So go through it, this one's, right? Right. After that, we have to draw the line parallel to this one's adiabatic saturation curve, like this one's. Here is now draw the line to y-axis, right? So this is the adiabatic saturation temperature TAS or which equal R TW, right? Variable temperature. So it's a 1, 2, 3, 4, 5. So 16, 16.5 or 16.5. degrees Celsius is the adiabatic saturation temperature. So after that point, you have to draw the straight lines here. This is called the dew point temperature. So it's almost the 16 dew point temperature. So TD. All of you got clear?
Yes, sir.
Okay. Please respond whenever I ask. Okay. Now moving to the cooling tower principle and operations. So here is a the cooling tower is a special type of the heat exchanger in which the warm water and air are brought in contact for evaporating cooling. Right. So it provide the very good contact of air and water in terms of the contact area, like contact area mass transfer coefficient and water vapor. Sorry, mass transfer coefficient of water vapor while keeping air pressure drop is low and enthalpy of air is lower than the enthalpy of waters. So here the schematic representation of the cooling towers. So here, one minute. The hot waters which coming from the heat exchanger is spread at the top of the cooling towers, right? And the air enter through the lavas. Here is a lavas. This is called the lavas. L O, right. So air enters through the lavas at the two opposite walls of the cooling tower. Here, yes, right. And the during the cooling process, the process of the waters around the 2% of water is evaporated. So here the makeup water used to compensate the evaporated water, right? So after and here is a humidification. So the means the heat remove using with the help of this like a drip and the cold water the hot water can get cooled and it cold water supplied for the heat exchanger or other applications like the simple phenomena. Clear or not?
Yes, sir. This is clear.
Generally cooling tower used to the whatever was the in the industry or industry the hot waters, so we cannot direct throw in the like any lake or rivers because uh, uh, it makes like a thermal pollution thermal pollution as well as it's harmful for the aquatic life. Cooling tower and reduce the heat reduce heat and that heat pass into the air and that cold water we can reuse for the other applications, right? So here is just a simple schematic representation of the cooling towers. So here is a blow down. So whatever the deposit stored at the bottom, so there so that should be that thrown outside the cooling towers. That's called the blow downs. Now here is a like a drift. 1 minute. So drips means whatever the we spread the waters at 1 minute. So the hot water spread at this plate. So whatever the droplet that can pass through with the help of this drift, and also yes, that's called the drift. So there are the different factors govern the operation of the cooling towers: dry bulb temperature and wet bulb temperature of air, then temperature of warm air waters, then efficiency of the contact between air and waters in terms of the volumetric mass transfer coefficient KYA, right? Then contact time between air and water, then uniformity of distribution of the phases within the towers, air pressure drop, and desired temperature of the cool waters, right? So based on that, after there are the types of the humidification equipment you have already studied. The classification of cooling towers. So based on the air drops, so it again classified like in classified such as the atmospheric, natural draft, mechanical draft. So mechanical draft again classified induced draft, forced drafts, and based on the air flow, it classified cross flow and counter flow, right? So based on that cooling towers, so here is some subjective questions. So it will get more clear with the help of this MCQ questions. So what is the primary function of the cooling tower in industrial process? So here is the options. You can tell the answers.
Option B, to cool water.
Right. I need to check it. How many students there? Right. Then second question, in a cooling towers, what is the term used for the water that is evaporated and lost to the atmospheres? Option given: drift, flow down, makeup water, and evaporation loss. If you know the answer, you can tell.
So it may be evaporation loss.
All right. Because drift, so you will see the drift and blow down also in MCQ questions. So it will get more clear. Question 3: which cooling tower component distributes hot water evenly over the fill media? So in cooling towers, this is called the water distribution systems. So in this question asks, which cooling tower component distribute the hot water evenly over the fill media, right? So option C. Are you getting this one?
Yeah, yes, sir.
Now next question, what is the terms for a process in which the water droplets are carried out of the of the cooling tower with the exhaust air? So what is the terms for a process in which water droplets are carried out of the cooling tower with the exhaust airs? So above the water distribution system, so there's I explain there is a drift, right? So drift used to carried out a water droplet, right, with the exhaust air, right? Like here is the water distribution systems. Here is the drift. The purpose of the drift is to carry out the water droplets with the exhaust air, like humid air. Next question, what is the purpose of the fill media in the cooling towers? The option given to increase the surface area for heat exchange, to reduce the water congestion, to filter out the impurities, to support the structure of the towers. You can tell the answer.
It may be, sir, to increase the surface area for heat exchange. Maybe.
Right. It is, yes, right, right. Because what else, like, any other unit operation process like pack beads, the pack means what is the means materials used. So that's increase the surface area and also increase the contact times. So this is the similar concept here. Increase the surface area for the heat exchange. If there is a more surface area, so there will be the more contact times. So there will be the more cooling of waters. Question is the blow down of the water from the cooling tower is done in order to. Option given: regulate the total dissolved solid, control the cooling water temperature, prevent the growth of algae, and none of the above. So, whatever the means hot water comes in the cooling towers, so there is a some like a dissolved solid, right? So at the in the during the process, so at the bottom, so there is a possibility of the deposited of the solid. So blow down means to regulate the total dissolved solid, to remove that the solid from the cooling towers, right? So option A, right. Clear or not?
Yes, sir.
So what does terms make up water refers to in the context of the cooling tower? So here option given: water added to replace losses due to the evaporation and drip, then water used to clean the towers, and water store emergency use, water used for the heating purpose.
So option A, water added to replace lost due to evaporation and the.
Right. So based on the MCQs, so we get clear idea about the cooling towers. The most important function in of lavas is to protect against the algal growth, to allow airflow while preventing the water splat out, uh, uh, and C, to enhance the structural strength of the walls, and D, all of this. So here is the lavas, right? Here is the water distribution systems. Like, so when we spread the waters in a droplet form, so it should not pass through the outside. That's why here the lavas are used, right? So, and the other purpose is to allow the airflow and while preventing the water splash out. Option B are. Question 9: which of the following is an appropriate driving force in the water direct contact cooling operation difference? Option given, so you can tell. Enthalpy, partial pressure, the temperature, humidity. Here is air water direct contact systems.
No, sir, I am not sure for this answer.
Here is enthalpy. We will see with the help of numericals. So how means driving force help here means enthalpy is a driving force for the air water direct contact systems. Question type: which type of cooling towers use fans to force or draw air through the structure? So here is a in this types cooling towers the fans use like mechanical drafts. So here is a the mechanical draft cooling towers. So in a natural draft means naturally means yeah, and hyperbolic cooling tower is also natural air flow. So in the mechanical draft, so fans used to flow the air. Question 11: which of the following is a major advantage of counter flow cooling tower compared to the cross flow cooling towers? So it's related to the heat exchanger like counter flow heat exchanger and cross flow heat exchangers, right?
A higher efficiency.
Right. Is a like water in, water out, air in, air out. So it's a higher efficiency. So in which question 12, in which type of cooling tower is a hot water sprayed over the film media and air is drawn upward to the film media? So here is already explained here. So hot water
Cross flow.
sprayed. Uh, no. It's the counter flow. Means one hot water sprayed over the film media here water in and air in and air is down upward, right, through the film media. So that's the counter
Right.
flow cooling tower, right?
Okay, right, sir.
What is the main advantage of natural draft cooling towers over the mechanical draft cooling towers? It's a simple question. You may answer this one.
Sir, answer option C. No energy for
Right.
conduction.
Fans, right. Now moving to the numericals. Use the calculators and try to solve. Did you attend the last class?
Yeah, yes, sir. Last class I was attended.
Okay. So the question 14 statement is the air at temperature 20 degrees Celsius and 750 mmHg pressures, total pressures has a relative humidity 80%. So what is the percentage humidity? The vapor pressure of water at 20 degrees Celsius is 17.5 mmHg. So you can try to solve the answer and tell me. So here given Tg given, total pressure given, right? Relative humidity given, these ones RAS, and vapor pressure given PAV, sorry, PA, right? So we have to calculate the saturation humidity, the percentage humidity. So percentage humidity equal to Y, sorry, uh, absolute humidity divided by humidity at saturation conditions into 100, right? So you can write down here the relative humidity given 80%. So you can write down directly 0.80 equal to 1 minute. No. And the relative humidity formula RH equal to partial pressure divided by vapor pressures into 100. So here the relative humidity given 80%. So you can write down 0.80 equal to PA by PEV, right? So we can write down in terms of the partial pressure and vapor pressures of these ones. Partial pressure divided by P by PEV. Sorry, vapor pressures of PA divided by total pressure minus vapor pressure of EA, right? Into 8 by 02 divided by 28.97, right? So it can 28.97. So it get cancelled, right? So moving to the here. So you can write down PA divided by PAV into P minus PAV divided by P plus PA, right? So here is a PA divided by P vapor pressure PA with a superscript V. So given 0.80%. So you can modify also RH, right? So divide by these terms by PA vapor pressures, like PV minus 1, right? P PEV minus RH, right? Means PA divided by vapor pressure, that's the relative humidity. So put the value here, RH 0.8, total pressure given 750 mm Hg, vapor pressure given 17.5 mm Hg. Put in this equations, you will get the percentage of humidity. All of you got clear? It's a 0.80 in 750 divided by 17.5 minus 1 by 750 1 so 17.5 minus 1 so 79.61%. So 79.61 of the percentage of humidity. Clear or not?
Yes, sir.
right? So here initially the percentage humidity formula y absolute humidity divided by humidity at saturation condition into hundreds. So here relative humidity given. So relative humidity is a partial pressure divided by vapor pressures into hundreds. So here is 0.8. So write down in terms of like mass ratio, right, mass ratio units. So PA partial pressure divided by P minus PA divided by vapor pressure divided by total pressure minus vapor pressure. So it will cancel, right? So after write down in these forms, so PA here, PA by 2PA is the RH, right? So I convert these terms into like this one's RH. Put the value, you will get the 79.61%. Next question, a cooling tower is used to cool the 500 kg per hour of waters from the 45 degrees Celsius to 35 degrees Celsius. The specific heat capacity of water is given 4.18 kilojoule per kg degrees Celsius. Calculate the heat removed by the cooling tower, right? Uh, W in, W denote for the waters 45 degrees Celsius and out at 35 degrees Celsius. W out. So after cooling, so how much heat removed from the cooling towers? That's us in these questions. So here the CP value given, heat capacity of water given, and specific heat. Right. So to calculate the heat remove, so formula Q is equal to M. This is mass flow rate, mass rate into CP heat capacity into delta T. Right. M CP into T I minus T out. So put the value, will get the heat remove. How much heat remove from the cooling tower? So M given 500 CP 4.18 into temperatures like CP degree Celsius. Check the unit also. 45 minus means 10. Right? It's a 2090 kilojoule per hour. You need to check the unit. kg per hour, kg get cancel, kilojoule per hour, right? Clear?
Okay, sir.
Question 16. The cooling tower remove the 25,000 kilojoule per hour of heat. The inlet air has a humidity ratio. Humidity ratio is absolute humidity, 0.01 kg of water per kg of dry air. And the outlet air is saturated at 40 degrees Celsius with a humidity ratio 0.03. So at outlet humidity, the latent heat of vaporization is 2400 kilojoule per kg. Calculate the air flow rate it is required. So here is the cooling towers, right? So here is the air in, here is the air out, right? So inlet humidity given y 0.01 kg water kg dry air. and here the sorry, that's the saturation humidity 0.03 unit is the same kg of water kg per kg. So here we have to the latent heat of vaporization given and cooling tower remove the heat means how much heat remove after cooling the waters here given that's it is smoothly. Yes. Here is a if I go to the back, so it automatically whatever I written down, it goes here is. So we have to calculate the air flow rate required, right? So like the formula to calculate Q equal to M air into latent heat divided by saturation minus Y humidity, absolute humidity, right? So here is the latent heat given, Q given 2500 and difference means saturation humidity and absolute humidity given. So put the value here. The latent heat vaporization at a temperature 30 to 40 degrees Celsius of waters, but latent heat of vaporization at 0 degrees Celsius 2500 kilojoules. So this is a latent heat vaporization for a temperature 30 to 40 degrees Celsius. 24 saturation humidity 0.03 minus 0.01, right? So calculate the EMA. It's a 520, 520.83 kg dry air divided by hour. Clear?
Yes, sir.
In last two questions, as I explained the concept, so based on that, you have to calculate it till the answers. That's a simple. Use the calculator. Cooling tower cools 800 kg per hour of water, removing the 33,440 kilojoule per hour of heat. If inlet water temperature is a 50 degrees Celsius, calculate the exit water temperature. Specific heat given 4.18 kilojoule per kg per degree Celsius. So here water flow rate given means how much heat remove given, inlet temperature given. So we have to calculate the exit temperature. CP given. Calculate and tell the answer. I explained the concept already in I think 17 means 15 questions. Question number 15. T in minus T out. Did you solve it? Just you have to put the value and you have to calculate.
Sir, I am unable to solve because I am outside from the home. Uh,
Okay. So currently you don't have the calculator.
yeah, yes, sir.
Okay.
Please explain. I
So
will solve it later.
okay. So T exist temperature is 40 degrees Celsius, right?
Yes,
So same concept here. Here you have to use a cooling tower is designed to the remove 50,000 kilojoule per hour of heat from the water, cooling it from 50 degrees Celsius to 45 degrees Celsius. Calculate the required of the water flow rate. Here we have to calculate the M, right? Here is a M Cp delta T, T in, T out, right? So Q given, Cp given, T given, T in given, T out given. Just you have to calculate the M, right? The mass flow rate means water flow rate is 1196.65 kg per hour. Is the water flow rate. Similarly, the question number 90. The cooling tower cools 600 kg per hour of water to 30 degree Celsius, removing the heat 30,000 kilojoule per hour of heat. Calculate the inlet water temperature, specific heat capacity of water given. Same concept. So here you have to calculate the inlet temperature. So T inlet is a 41 kg per to mcp Ti T outlet given 30 degrees Celsius. 1 minute, I'm calculating. 41.96 degrees Celsius. Now moving to the question number 20. A cooling tower is used to cool the 1000 kg per hour water from 40 degrees Celsius to 30 degrees Celsius. The specific heat capacity of water is 4.18 kilojoule per degree Celsius. Calculate the heat removed by the cooling tower and amount of air required if the inlet air is a 25 degrees Celsius. Has a humidity ratio 0.01 kg water kg dry air. The outlet air saturated at 35 degrees Celsius. So in this question, we have to calculate how much heat removed from the cooling tower and amount of air required. Like here is a cooling tower. Air in, water in. A denote for air and W denote for the water. Air out, water out. Right. So cooling tower is to cool the flow rate given 1000 kg per hour water from 40 degrees Celsius to 30 degrees Celsius. Right. And heat capacity given 4.18. Calculate the heat remove. So you can calculate the heat remove with the help of this equation M Cp dt. Right. So first calculate these ones. So M given 1000 Cp 4.18 into temperature difference is a 10. So Q is a 4180 kilojoule per hour, right? So that's the heat removed from this cooling towers. After that means how much amount of air required to cool the waters. So to calculate this ones, here 1 minute. The given humidity ratio given Y means absolute humidity 0.01 kg waters to kg dry air, and the outlet air saturated at 35 degrees Celsius temperature given only here, right? To calculate the amount of air required, so you have to use this formula, m air into here is a latent heat of vaporizations into difference of humidity, right? To so latent heat of vaporizations is a 2400 kilojoule kg, right? Unit same, right? Kilojoule per kg. To calculate this difference, we know the final condition, final and initial condition. So here only given the initial uh, humidity 0.01, but we don't know the humidity at the after the saturation, right? So here we have to use the stoichiometric chart. So at this temperature 35 degrees Celsius, 35 degrees Celsius, and initial temperature this one's 0.01. So I can go. The outlet temperature is it's 35 degrees Celsius. This one's 30. Here is a 1, 2, 3, 4. So one line is a 2.5. So is a 32.5. Is a 35, right? And humidity at initial conditions. This one's so go upward. So I have to calculate the saturation conditions, right? So now we have to draw the parallel line with this ones like adiabatic saturation curve line. So similar this ones. Not a parallel. So after that touchings, like the other straight line toward this secondary y-axis, like straight. So it's around 1 minute one. Outlet temperature 35 degrees Celsius. 32.5, 35. If I go straight, it's wrong. 0.035. 0.05, 0.03. So it's a 0.015. So why? Yes, it's a 0.015. Move to the question number 20. So why? Yes, humidity or saturation conditions got 0.015, right? Kg of water, kg of air, right? So we have to calculate here MAR, this ones. We already calculated the heat remove. So if I go back, so automatically it erases. Let's see, so here. So Q M air into latent heat into difference of humidity, right? So humidity difference is 0.015 minus 0.01, right? It's 0.005, right? Units the same kg of water per kg of dry air. So put it in the equation, you will get the amount of air required. So EM here now latent heat of vaporization at this temperature 30 to 40 degrees Celsius is 24 kilojoule per kg, right? Here is a difference. So you will get 41800. We calculated in the first part of this questions. 41800 heat remove 0.005 into 24. So M rate is a 348.33. Unit is kg of dry air divided by hour. All of you got this? Clear it? So initially we calculate the heat remove from the cooling towers with the help of Q is equal to MC M into Cp in delta T. So after getting that heat remove, so then you use this formula Q is equal to M air into latent heat of vaporization into humidity difference. So we know the initial humidity 0.01. So after saturation we don't have, so we have to calculate at these temperatures with the help of the stoichiometry charts. So that got the value 0.015. Clear or not? Mohsin, am I audible?
Yeah, yes, sir. Yes, sir.
Moving to the 21 question number 21. The statement here: the air sample air has a sample of air has a dry bulb temperature 32.5 degrees Celsius and humidity 0.015 kg of water per kg of dry air. The total pressure is atmospheric, means 1 atm. The entire equation for the water is ln Pa with a unit bar. This is a equation given, right? I answered the following question. The first determined determined the stoichiometric properties like relative humidity, dew point, adiabatic saturation temperature, variable temperature, and enthalpy, humid volume, and humidity. Right. So here at Tg given, humidity given, total pressure given, and this equation given. So first we have to calculate the relative humidity. Here you have to use the formula and calculate the this psychometric properties. Right. So first the relative humidity, RH. The RH, the formula is partial pressure divided by vapor pressure into 100. Right. So here humidity given. The absolute humidity Y equal to P partial pressure divided by P minus PA into 18.02 28.97, right? So first we know the sorry first we here calculate the partial pressure using this equation. So yeah, because here humidity given 0.015, so you will get the partial pressure. Total pressure is a 1 atmosphere. The here is a unit of the pressure is a atmosphere, so you have to convert it. So 1 atm equal to 1.013 bar, right? So put this y value here 0.1, so you will get the partial pressures. So I already calculated partial pressures is equal to 0.02385 bars. Whenever you are not understanding, so you can ask, right? Partial pressure. Now need a vapor pressure to calculate the relative humidity. So here is a temperature given 32.5 degrees Celsius. So here is the unit of the in this equation the unit of temperature is the Kelvin. So first convert this temperature into Kelvin. So T is equal to 32.5 plus 273.2. It's 305.7 Kelvin, right? Just we have to put this value in this temperature, so you will get the vapor pressure value, right? So I calculated already PA equal to 0.0489 bar, right? So we got the partial pressures and the vapor pressure value. So we can calculate the RH. So RH equal to 48.74%, right? This is the first part. Now we have to calculate the dew point. So we can calculate the dew point using this stoichiometric chart as well as as a numerical means like based on the equations, right? So dew point at the dew point the partial pressure equal to the vapor pressure, right? Partial pressure equal to the vapor pressure. It's 0.02385 bar, right? So you have to use this pressure value in these equations, so you will give the temperature value, right? So that's the dew point temperatures. Is that the dew point? So I calculate. So first calculate the. Sorry. Using this equation, you will get the temperature equal to 293.5 Kelvin in degree Celsius, 20.3 degrees Celsius, right? So now, so using this like temperature and humidity, we can calculate the dew point by this stoichiometric charts. So it is a 32.5 temperatures. Right here is a 1, 2, 3, 4. So one each means 2.5. So it's the first one, right? Humidity given 0.015. So I can draw the line, right? So from this at these points, now we have to draw the parallel line like this one, adiabatic saturation curves till this 100% saturation humidity, right? So we will get this adiabatic saturation temperatures, and the other straight lines till 100%. So these temperature is the adiabatic saturation temperature, or which are at wettable temperature, because adiabatic saturation temperature is equal to the wettable temperature. So either TAS or TW. This temperature is a dew point. So it around almost 20 point something. So clear or not?
Yes, sir.
Right. So calculate the adiabatic saturation temperature. This one's adiabatic saturation temperature. 1 minute. Here is a 5, so 22, 24, or 25, around the 20 points. So TAS is a 25 to 26. If I written here, I can write here the range 25 to 26 degrees Celsius. So there are adiabatic temperature, adiabatic saturation temperatures. Next is a wettable temperature. So it's equal. So TW same. Right. Now next term, next is the enthalpy, humid volume, and humidity. So we can calculate with the help of this stoichiometric chart, and also using this equation. There means the different way to calculate this uh, stoichiometric properties. Like next is the enthalpy. So here is the formula given: uh, humidity into latent heat plus Ch Tg minus T naught. So you have to put the value in this equation. So you look at the properties. So here is a 0.015 latent heat. So which value you have to use here? Latent heat of water. So latent heat of vaporization at 0 degree Celsius, its value is a 2500 kilojoule per kg. But latent heat of uh, vaporization at temperatures like 30 to 40 degrees Celsius is a 2400. Right. So CH. So the CS here is a relation bar. The CH means humidity 1.005 plus 1.88. Here is a humidity. So humidity 0.015. Put in this equation. So TG given variable temperature 32.5. and T naught is equal 0, right? So enthalpy is a 70.079 kilojoule per kg, right? Next is a humid volume. So here is the given the equation. Just now you have to put the value in here. So VH is equal to 0.8860 meter cube per kg dry air. Next property is the humidity. So here is the equation given. So CH is equal to 1.033 unit is kilojoule per kg dry air into Kelvin. Kilojoule kg dry air into Kelvin, right? So we calculate all the properties. Now statement is the same, but we have to calculate the different so in same statement, but here if the sample of air is heated 40 degrees Celsius, what will be the weightable temperatures? So here the weightable temperatures mean TW, right? So it is a 40 degrees Celsius given, right? So here you have to use the stoichiometric charts. So humidity is 0.015, same. The 40, right? Just have to draw the parallel line, just like this, similar to this one. Draw for the so this is the your breathable temperature. So how much? 22, 24, 26, right? Clear?
Yes, sir.
And if you have to calculate the dew point, how can you calculate? Can you tell the answer? I already explained. So you have to draw the straight line from this point toward the primary y-axis till 100% humidity. It's like that is your the dew point. In this question, not purpose information. I am telling this one. This is a TD. Almost 22 point something. Your weightable, sorry, dew point temperature. In the third part, how much heat is rejected if 1 kg of dry air is cooled down 32.5 degrees Celsius to 15 degrees Celsius? So in this, we know the humidity at the 32.5 degrees Celsius. So we have to calculate after saturated, means right. So after saturated, you have to calculate the humidity, right? So here you have to use the no. So here you have to use the this Anton equations. So first calculate the vapor pressures up 15 at 50 degrees Celsius, right? Then we can calculate the saturation humidity. right? PAV divided by P minus PAV into 18.02 divided by 28.97, right? So first put this convert degree Celsius into kelvins. So you will get PA. So I already calculated 0.0168 bar, right? So put in these equations, so we will get the saturation humidity. 0.0105 unit kg of water kg of air, right? So you know the initial conditions y at starting humidity absolute, right? Tg. So here you have to calculate the air enthalpy equal to latent heat into difference of humidity plus Ch into Tg minus T naught. Here Tg is a 32.5 and T naught is a 15 degrees Celsius, right? So here latent heat of vaporization 2400, difference here the condensations occur like 0.015 minus 0.0105, right? Ch to calculate the Ch humidity, so there is a formula 1.005 plus 1.88, and here is a absolute humidity y 0.015, right? And temperature is a 32.5 minus 15 degrees Celsius, right? So that's the Talpi
So
28
last one,
point
32.5 minus
sorry
32 point
sorry
first minus last one
32.5
T
minus
naught is
15 degrees Celsius, 15 this one, here
15.
is a,
Oh, oh.
so 28.881, so kilojoule kg of dry air, right? So heat rejected if 1 kg of dry air is cooled down the 32.5 degrees Celsius to 15 degrees Celsius. So initially we calculate them is how much heat rejected. So that concept can you use here. H equal to, but we have to know the flow rate of water, like m air into, so you have to know the m air. No, we don't, this concept we are not using in here. This is clear or not? Moving to the fourth part of these questions. If the air sample is heated, the statement is the same, so that's why I'm not reading this ones. If the air sample is heated at to 40 degrees Celsius and its pressure double, means total pressure is double. So what would be that's the relative humidity and dew point? So first, you have to calculate the vapor pressure at 40 degrees Celsius. So I calculated here PAV is equal to 0.073 bar. Because we have to calculate the relative humidity. Relative humidity formula is partial pressure divided by vapor pressure. Right. Now we calculate I think first part partial pressures 0.023 bar. Right. But in this question, we mentioned that pressure is double, means P is twice the pressure, right? So double total pressure is double, so partial pressure is also double, right? Because the total pressure is a partial summation of partial pressures of constitute like PA, P, V, right? So so partial pressure become a double, so it's a 0.0046, right? Now put this value. This equation PA divided by PAV, right? So with this way, you have to use this value. So relative humidity is a 63.01%, right? Similar. Okay. Next part is a dew point. So same question. So you have to add partial pressure equal to PAV equal to 0.046. So you have to use this value. Put in this entire equation, so you will get the temperature. That's called the dew point. So this is one approach. Another approach is you have to use this at temperatures, and since okay. So at these temperatures, so you can we have so the such vapor pressure. So we can calculate the saturation humidity. So based on that, we can calculate the dew point with the help of the stoichiometric chart. Now moving to the last questions of today's sessions. The statement is given: a cooling tower is used to be designed to cool the water from 45 degrees Celsius, 30 degrees Celsius by the counter current contact with the air of dry bulb temperature, wet bulb temperature of 25 degrees Celsius, humidity of dry air. The water rate is given 5500 kg per hour per meter square, and air rate is 1.25 times the minimum. The overall mass transfer coefficient is Ky A equal to 2500 kg per hour per meter cube. The slope of operating line touching with the equilibrium line, the slope of tangent is 8.78, and CWL given heat capacity 4.187 kJ per kg per Kelvin, and number of transfer unit NTG given 6.14. So in this question asks a dry air flow rate to be used, then height of the packing, then wet bulb depression at the bottom of the towers. So here is a cooling tower with given conditions. Counter 100, A in, air in, W in, A out, plus W out, right? So cooling tower is designed to cool the 45 initial temperature 45 degrees Celsius, final 30 degrees Celsius. All right. And TG temperatures given 30 degrees Celsius, right? And humidity given Y, absolute humidity 0.019 kg of water per kg of dry air, right? The water rate given, so that denote for the L, this 155 kg per, right? So we have to calculate the air flow rate of the air, right? Now here is the slope given, right? So here is a relation L into CWL DTL equal to GS DH. So here is a L is a water flow rate unit kg per meter square second. CW is a heat capacity. D is the temperature difference of waters, and GS is the air flow rate kg of dry air per meter square per second. This is the enthalpy difference. Yeah. So here is the slope given. 1 minute. 8.78. So slope is a dh by dt, right? If you draw the uh, graph h versus t, right? So here is a like equilibrium line, here is the operating lines, the tangents from this point, right? Here in condition 1, in condition so that's a slope dh by dt, so which equal to LCWL divided by GS. Look at this one. So slope given 8.78, right? And L given 5500, and the height capacity given 4.187. So we will get the GS minimum one. Here is GS minimum. So GS minimum equal to L 55 to 4.18 divided by slope, this one 8.78. So GS minimum equal to 2623 kg meter square per hour, right? But here mentioned that the air rate is a 1.2 times the minimum, right? So actual air rate equal to 1.25 into this one's 2623. So it's 3279 kg meter square per hour, right? That's the actual air rate. That's the first part. Now second part, the height of packing. So here is a formula given to calculate the height of packing. Z is equal to STG. STG means height of the gas enthalpy transfer unit. NTG means number of gas enthalpy transfer unit. So here is the NTG given 6.14. Now you have to calculate the STG using this formula. So here GS we just recently calculate 3279 3279, and here is the mass transfer coefficient is given Ka 25, right? So it's 1.3116 meter, right? So you know the we already given that NTG. And calculate the staging, we have to put in these equations. So Z is a 8.05 meter. So height of packing is a 8.05 meters. Clear or not?
Yes, sir, here.
Next is a wettable temperature. In the last class, I already explained the wettable differentials. The wettable depression is a Tg minus Tw. Guys, here is a T given 30 degrees Celsius and the wettable temperatures is a 25 degrees Celsius. So we have to put this value here 30 minus 20, 25. So 5. This is a wettable depression. This is the part C. So I cover all the questions based on the cooling towers and use of the stoichiometric chart. If you have any doubt, please ask.
Thank you, sir.
No question. So okay, thank you for joining. So I'm going to conclude today's session. So we will meet on next Friday, same times on a next step, next chapter like drive. Okay, thank you.
Okay, okay. Thank you, sir.